Anyway, so let's briefly. Let's briefly recall where we are. We now had to construct a commutative differential graded algebra starting from a polyhedron. And moreover, this algebra is quasi-isomorphic to singular cochains as a DGA. Well, this one is commutative, this one is not commutative, so that's all one can hope for. One question that comes to mind, and what happens if X is not a polyhedron? If X is not a polyhedron, then there is still a way to associate a commutative differential graded algebra to it by taking the APL of the singular of the geometric realization of the singular simplicial set. This thing is enormous, but it's weakly homotopy equivalent to X. The advantage of this construction it's functorial in X. But from purely computational perspective, both the APL of X and the APL of the sing of X are untractable. They're both very large, and we can't really deduce anything by looking at those algebras directly. So we need something more tractable. And today we will see how to construct, starting from a CGGA, how to construct something more tractable, namely the minimal model. And later on we will prove that those minimal models are unique. So we define a minimal model, and then later on we will prove that those are unique up to isomorphism. So once we've done this, we will be able to talk about the minimal model. So from now on, we will consider. Okay, before I talk about models, let me just say that we. We will only consider CDJs which are non-negatively graded and the zeroth cohomology will be the ground field. Now we've run out of chalk. That was predictable. Well, can somebody maybe see some chalk hiding somewhere? Плохой, да. Хороший круглый, плохой квадратный. Ну, точнее наоборот, круглый хороший, квадратный плохой. Да, ну, в общем, была полная, знаешь, как в частушке поется, была полная коробочка. Вот, значит, а теперь совсем пусто. Так, значит, Миш, есть ли у нас продвижение? Well, thank you very much. Yes, well, it'll do for I don't know, half an hour or so. Anyway, the minimal model. is a quasi-isomorphism from M to A, where A is the CTJ that we want to model, such that number one, M is free. Meaning M is the free algebra on some graded vector space as free as an algebra. As a graded commutative algebra. And secondly, the differential is decomposable. Which means the image of every element of V under the differential can be written as a product of as a sum of products of the generators. One thing we want to avoid is the image of a generator being another generator. And let's also include the requirement that V is non-negatively graded. Well, in practice, those minimal models are not too difficult to construct. Let's consider a few examples. Let's take the differential forms on some polyhedron let's take either some polyhedron which is homotopy equivalent to Sn or homeomorphic, or the big version, meaning the geometric realization of the singular simplicial set. for order n, the answer is completely straightforward. We just take the exterior algebra on one generator which lives in degree n. Now, inside this algebra, there's a class which and the differential is 0. Inside this algebra, there's a representative of the fundamental class. We just take x to this representative, which can be chosen arbitrarily, and all conditions are satisfied. A slightly more difficult case is when n is even. In which case we have two generators. Let's call them x and y. X again represents the fundamental class, or more precisely, x lives in degree n, and under this comparison map, it goes to the fundamental class. But then x squared is non-zero. X squared is 0 here, but not here. So we need something which kills x squared. Well, let's call this something y. Now, an easy exercise shows that the cohomology of this algebra is the same as the cohomology of the sphere, and well, clearly the map is an isomorphism, so we have constructed a model, and by inspection this is a minimal model. In the same way we handle, for example, the complex projective space CPN, in which case M is again generated by two elements, but this time they will live in degrees 2 and which degree? To n plus 1, yes. So dx is 0 to y is x to the n plus 1. And for similar reasons, we conclude that this is a minimal model as per the definition. These examples show that although the algebras we try to model are quite large. The minimal models are not as large as the algebras themselves, and they are more tractable. So let's state two theorems about minimal models. Say again?
We need a quasi-isomorphism in algebras. We know that homologies are isomorphic, but we need MI.
Yes. So
y to 0, yes?
y goes to let's see. So this thing has a dimension, has a real dimension to m. So there are no two n plus 1 forms on it. So yes, y goes to 0. The first theorem the first theorem says that every CDJ has a minimal model, and the second theorem suppose we have a simply connected space. Then well, for simplicity, let's assume X is a polyhedron. Then by definition, the minimal model of APL is is free on some graded vector space. A Q vector space. By the way, recall that APL is over Q. Okay, so what is a graded space? A graded space is a collection of just vector spaces, which is indexed by, well, in general by integers, but in our case by integers which will be greater than or equal to. Now, the statement of the theorem is as follows. Vi is isomorphic to pi I of x tensor Q dual. In particular, if all groups are finite dimensional, have finite rank, then basically there is an isomorphism, a non-natural, but an isomorphism nonetheless, between Vi and Pi tensor Q. So, in other words, once we know the minimal model, we know the ranks of the homotopy groups. For example, CPN has only two homotopy groups which have a free component, and these are the second one and the n plus first one. Are there any questions? So once again, the point of constructing minimal models is firstly they are constructible, and secondly the generators of those are one-to-one with the generators of the duals of the homotopy groups, tensor Q. Okay, now let's call this theorem 1. This will be theorem 2. Well, let's prove theorem 1. So we start with the CDGA, which which has only which has cohomology only in degree 2 or higher. And well, in degree 0 there's the ground field, but nothing in degree 1. Basically, after we've understood how this works for degree 1, for in the simply connected case, the general case will be similar but messier. we will construct the minimal model by induction. We start with the second stage, then we'll construct the third stage, and then the fourth stage, and so on. And then we'll just take the direct limit, and this will give us the model. Okay, now those stages aren't arbitrary. So let me explain what exactly we want from those from those algebras. So we want. Let me call this this map Fn. Fn induces an isomorphism in degree n or less, and an injection, an injective map in degree of cohomology in degree n+1. Okay, so Mn, let me every Mn will be free, and the generators will be in degrees greater than or equal to and less than or equal n. Well, the base case is very simple. We just take the second cohomology space, and we put it in degree 2. No surprises there, and we generate a free algebra using this space. well, the map F2 is clear. We just take we just take a basis. We choose a representative for each element of the basis, and we take this element of the basis to its representative, then extend by Q-linearity. No surprises. And we do have an isomorphism in H2. We also have an injective map in H3 because this algebra has nothing in degree 3. Okay, so we have both properties. Now let's go one step further. Let's construct the inductive. Let's describe the inductive set. So suppose we have we have somehow constructed Mn, and we want to construct Mn plus 1. Okay, now what do we have? Well, firstly, we have this map, and it's injective, but it's not an isomorphism in general. So let's take the co-kernel and call it C. We also have the map in degree n plus 2. This map is not guaranteed to be either injective or surjective, it's just a map. So in particular, it has a kernel Well, let me call the kernel K. Does everything make sense so far? Okay, so the kernel, the co-kernel. Now I want to define mn plus 1. Okay. I take the co-kernel, and the co-kernel lives in degree n plus 1. Well, and then I take the kernel, but I want to shift it 1 degree down. So instead of taking just the kernel, I take the kernel shifted downwards by 1. Now I need to define the differential. On the kernel, I just declare the differential to be 0. Now, what about the other summand, the kernel? Well, what is it? And so we have the map from K to n plus 2, no, n plus 2 of Mn. Well, this map is injective. Now, let me take a lift, meaning just by linear algebra, once I have this map, I can lift it to the cycles, or co-cycles, which live in degree n plus 2, and the whole thing, which will be in degree n plus 2 in M. So we have this map which is a lift of this map, and then we take k minus 1, a linear isomorphism k plus 1, a linear isomorphism k of 1 to k to the co-cycles to m plus 1, and this will be the differential. Why is d squared 0? Well, if I apply d squared to an element of k, I end up here. But these are cycles, or co-cycles. So when I apply d again, I get 0. Does this make sense? Okay. And d on Mn, the differential is the same as well, the same as before. Okay, so we have defined the differential at least on every generator. Now, my claim is once I have defined the differential on these generators, and I've checked that d squared is 0, this gives me a well-defined differential on the whole algebra. So exercise this does indeed define a differential on n plus 1. Okay. Now I need to construct a map from mn plus 1 to a. Again, I only need to define the map on the generators because the algebra is free. Okay, um, we have C, which lives in degree n plus 1. So Hn plus 1 surjects onto C, but we are in Q vector spaces, so we can split the surjection. And then we lift this map first to cycles and then to well, the cycles are a subspace of the whole thing, to the whole of A n plus 1. Does this make sense? Say again?
We can do the split because it is a Q vector space, so kernel plus Hn plus 1 of M is Hn plus 1 of A.
Yes, this arrow splits non-canonically because everything is free. So we take some splitting, doesn't matter which one, and then we lift cohomology to co-cycles in some way, and then co-cycles are inside An plus 1. And I've run out of chalk again, so thank you very much. Okay, so we need to extend the map to K of minus 1. What do we do? We basically recall the construction, the definition of K. Oh, sorry, K1. It's very confusing. basically every element of K goes okay, so every element of K goes to 0 in so we have K. Every element of K is a cycle which goes to 0 in the cohomology of A. So we have firstly, let's take an element of K. Let's lift it to the m n plus 2. Sorry, it's in degree n plus 2, so n plus 1. Okay. n plus 2. Firstly, we lift all elements of K to elements of Kn plus 1. To elements of Mn. This is possible. Basically, we choose again a cochain which represents a cohomology clause. So take a lift, then we apply the map into A. Every element here becomes a cocycle, well, a co-boundary. So we have this map. Does this make sense? And this is the differential. Now I need to prove that the map Fn plus 1 well, by inspection, the new generators live in degree n plus 1. So this condition is true. But I need to check the first condition, namely namely, I need to prove that in degree n plus 2 I have an injective map, and in low degrees I have an isomorphism. And to see this, I want to represent the algebra Mn plus 1 as follows. I want to represent this algebra as a spectral sequence, which of course doesn't make sense, but at least not literally. But still it's helpful. So we have new generators in degree n plus 2. Sorry, n plus 1. What's important is I have nothing in degree. I have nothing in degree 1 for m. M only has generators in degree in degrees between 2 and n. So this is in degree n plus 1, n plus 2. Well, from this picture, it follows that let's calculate the cycles of mn plus 1 in degree n plus 1. Firstly, we have the cycles which were there before. And we have some new cycles. The new ones are C. Does the picture make any sense? well, formally, what I've done is I've calculated the cycles of mn plus 1 in degree n plus 1. Well, by looking at the picture. We'll also need this. There's 0. This is the group which lives in by degree 0 n plus 1, and to the right and on top of this group we have nothing, we have zeros. Okay, now does what's happening make any sense? Well, there's a 0 here because what I have in cell PQ is the degree P part of M times the degree Q part of this thing. And the degree 1 part of M is 0. Why? Because M has no generators of degree 1. And this is important. This is why everything simplifies when H1 is 0. Okay, so we have some new cycles, and we have no new. We have some new co-cycles, but no new co-boundaries. Oh, sorry, it's supposed to be an N. The co-boundaries in degree n plus 1 are precisely those which come from M. The co-boundaries of Mn plus 1 are the same as those in Mn. So the cohomology of Mn plus 1 is the same as, in degree n plus 1, is the same as the cohomology of Mn plus C. Okay, so let me see if this suffices for the induction step. Well, I also need to know something about cohomology in degree n plus 2. So in degree n plus 2, Well, I'll erase this part. In degree in degree n plus 2, we have no new cycles whatsoever. Sorry, n plus 1, mn. But we have some new co-boundaries. We have new co-boundaries, namely we have the old co-boundaries in degree n plus 2, and then, but we have an extra k. So the cohomology of in degree n plus 2 of mn plus 1 is the cohomology in degree n plus 2 of mn quotiented by k. So we have eliminated precisely the classes that go to 0 under the map Fn, and we've added precisely the classes that were missing in degree n plus 1. So this and this together imply that Fn plus 1 is injective in degree n plus 2 . And as an isomorphism in lower degrees. Are there any questions? Ну, потому что если бы в первом столбце были не нули, то тогда у нас бы вполне могли появиться значит, новые кограницы вот здесь. Значит, Ну, первый столбец все портит. Значит, давайте посмотрим. Значит, у нас, если бы здесь стояло что-то, значит, то так, значит, ну, оно, да, значит, оно бы вот эти не испортило, потому что сейчас, но оно все равно много чего испортило. Сейчас давайте подумаем.
Ну, мне непонятно, да, почему какая она быстро вырастает, какие-то штуки, у которых сложные чудеса, происхождения.
Значит, смотрите, вот если у нас здесь, значит, сейчас, да, значит, если у нас здесь что-то, то тогда оно, значит, оно будет приходить, то есть оно будет давать вклад в да, значит, оно будет давать вклад в только n плюс 2. Значит, дальше, значит, мы уже не сможем сказать, что значит, циклы вот здесь будут одинаковые. И, соответственно, нужно будет разбираться разными вопросами, и с ними можно разобраться, но давайте сначала поймем простой случай, а потом значит, скажем, что, то есть тогда будет понятно, там, за что мы будем бороться в сложном случае. Okay, well, I've just said that if we have something other than 0 here, then we can no longer claim that the cycles are the same, which complicates things, and we'll later see how to handle this problem. Okay, are there any more questions? Are there any people who need to go to the independent university afterwards? Okay, there are still those people. Anyhow, okay, so let's have a break, and then we'll continue and maybe prove the second theorem. So before we continue, I would like to add that the proof I've just given can be found in bottom 2. And the section is the number of the section. I don't remember, but the title has a rational homotopy in it somewhere, and so it's easy to find. Now, before we start proving theorem 2, let's look at the proof of theorem 1 from a slightly different viewpoint. Why? Well, because we would like to be able to apply similar procedure in other situations, and let's try to understand all this in a more conceptual way. The proof we just saw is a minimalist version. So something less minimalist. So first of all, let's recall the following the following thing. So suppose we have a chain map of two complexes. Then there's then there is the cone cone of F, which I would like to So if I want to if I want to have a short exact sequences of complexes, I have to put a cylinder here. Now, let's see if it makes sense. So for chain maps, there are notions of the cone and the cylinder, and basically these are very very similar to the same notions for spaces. Let's see. So I want to turn this map, which is just some map, not necessarily injective. I want to turn this map into an inclusion. Okay, so who remembers the definition of the cone of a chain map? Well, I want to have this this map, the inclusion of F into the cylinder to be of degree 0. So the cylinder would need to contain two copies of what? Of C1 or C2? Well, since we want this this map to be injective, two copies of C1. So C1. C1 shifted by 1, and plus C2. Let's see if this makes sense. I want this this map to be a homotop equivalence, and no, I want this this thing to be homotop equivalent to the second complex, and okay, so I've messed up the. Okay, so I've messed up the indices. Okay, so let me put C2 plus C1 and C1 shifted by 1. And the well, basically, let me erase shifted by 1. I have maps from here to here, from here to here, and this gives me a double complex. Now the okay, this this double complex, which anyhow, let's let's see if there is an easy way to check whether or not this works or doesn't work. anyhow, let's assume this works. Although I may have messed up the formulas. Now, once we have a double complex, we can form a total complex, and this is what people normally call the cylinder. The strange signs in the definition of the cylinder come from an essentially arbitrary choice for the signs in the total complex of a double complex. Okay, so the and once we have the cone, we have the quotient, which is once we have the cylinder, we have the cone. Another reminder. Suppose we have a cochain complex. Then there is the canonical filtration on this complex. In degree n. Oh, sorry. Let's call this I. Ci, if I is less than n, the kernel of the differential di or dn if I is n, and 0 if I is greater than n. So the tau less than or equal n is always a subcomplex of the complex C, and the the induced map is an isomorphism. The induced cohomology map is an isomorphism in degrees less than or equal n, and is 0 in higher degrees. Okay, now now we we can construct, we can reinterpret the construction of m n plus 1 starting from mn. Namely, let's take Fn from Mn to A. Let's forget about this. Let's forget about the fact that this is a map of algebras. Let's just consider it as a map of complexes. Where does the cohomology of the cone start? In degree n or less, we have an isomorphism. In degree n plus 1, we have an inclusion, an injective map. So the the cohomology of the cone starts in degree, in which degree? Yes, so we have n plus 1 for mn, n plus 1 for A, but to the left, this map is injective, so to the left of it there is a 0. Okay, so so the the cohomology of the cone is 0 in degrees n or less. Well, let's truncate this is called the canonical filtration or the canonical truncation. Let's truncate the cone canonically in degree n plus 1. Well, just by looking at the long exact sequence which corresponds to this short exact sequence of complexes, what do we have? We have the kernel. We have C plus K 1, where K is C is the kernel in degree n plus 1, and K K is the C is the co-kernel. K is the kernel in degree n plus 2. So the space of new generators C plus K shifted by 1 is precisely the truncation of the first non-trivial truncation of the cone. And, let me call this this space X. Okay, now I want to construct, not construct, reinterpret. Mn plus 1 as a push out of the following diagram. And the trouble is, I think I've messed up the indices again. So let's have a look. Well, the cone of X is the cone of the identity of X. I want to have a map from the cone to Mn and instead I have a map from a shifted cone. Let's think a little. Okay, well, it doesn't matter. Let me put a shift here. Let me check again if I messed up the indices. Okay, so okay, so this one is correct, but what what I need here is x shifted by 1 plus x. So the basically this thing should be should contain one copy of the shifted x and one copy of just x. Okay, so does this make any sense? Это все нужно для того, чтобы строить минимальные модели в похожих случаях, значит, но более сложных, когда у нас не совсем все на тку. So there are three options. None of option 1, none of this makes any sense whatsoever. Is this the case? The map is 0. This one is so this Okay, so this one is 0, so this one is 0 too. Basically, we constructed the x. Let's be more careful and say homotype equivalent to 0. We constructed the x so that x minus 1 to m to a would be 0, at least in the derived category. So let's forget about the truncation. We have this map. To the right of it, we have the cone, and to the left of it, we have the shifted cone. And when we go from the shifted cone to Mn and then to A, we get 0. And then when we truncate, we also get 0. Так, значит, вместо того, чтобы что-то прояснить, значит, это все только всех загрузило, я правильно понимаю? Значит, зачем это все нужно? Значит, затем, что значит, мы не всегда можем пользоваться расщеплениями. We cannot always use splittings, which is very convenient when we can, but there are many cases where we cannot. There is always a way to include any map of complexes into a map of in what some people call a distinguished triangle. Even if we cannot use splittings, there is a way to adapt this procedure. This functor and this functor makes sense for complexes of not necessarily vector spaces, but for basically arbitrary complexes of objects in an abelian category, which is why we're talking about it in the first place. Итого, значит, для построения минимальной модели характеристика 0 не нужна. Значит, точно таким же образом мы можем построить минимальную модель для, там, допустим, по крайней мере, вот насчет минимальности не уверен, но насчет кофибрантную модель для, например, симплициальных коммутативных алгебр над любым кольцом. Значит, и это иногда полезно. So anyway, what I've just said can safely be ignored if one is only interested in the rational homotypy theory. Are there any questions, comments, remarks, criticism? Now, let's sketch a proof of theorem 2. In theorem 2, we wanted to prove that the generators of a minimal model are one-to-one with the dual spaces of the rational homotopy groups. Well, the key remark is the construction of Mn mimics the Postnikov tower. To make this more precise, we if A is APL of X where X is simply connected, then Mn Mn is a minimal model for Xn. But this alone doesn't give us the homotopy groups. We have two spectral sequences. the Ray spectral sequence for this vibration, and another and another similar one which converges to the cohomology of m n plus 1. And these are isomorphic, and the E2 term of the starting from E2 and the the E2 term of this one of this one is isomorphic to P n plus 1 tensor Q. Or is it the dual? Which one is it? Let's think. Let's forget about mn plus 1. Let's just consider the Ray spectral sequence of this. What's the E2? What's the E2 term? It's the cohomology. Rational. Everything is rational. So we have the cohomology of the fiber, which is k pi n plus 1, n plus 1. This is the fiber of this map, Q. And what is it? It's the same as pi n plus 1. Pi n plus 1 Q. And this is, let's see, so Hom pi n plus 1 Q. My claim is this is the same as pi n plus 1 tensor Q dual. Now, let's see. First of all, to conclude this, we use the universal coefficient theorem. The cohomology of something with Q coefficients is Hom from the homology to Q. And plus some x. Now, why does x vanish? let's think. And does it vanish? Maybe it doesn't vanish. Okay, sorry. N plus 1. Так, вспоминаем универсальные коэффициенты. Значит, возникали ли универсальные коэффициенты? Возникали. Ну, давайте вспоминать. Значит, что там, что у нас стоит? Q, ну, смотря над чем. Сам над собой проективный, над Z совершенно не проективный. Да, но нам здесь проективность не нужна, значит, Q не активный. Значит, ext пропадает, когда первый аргумент проективный или когда второй неактивный. Если так вспомнить. Вот, значит, если мы будем брать x наоборот из Q куда-то, вот тогда может получиться, значит, что-то там, в общем, какое-то безобразие. А вот, значит, откуда угодно в Q, там все, значит, там все окей. So the first equality is the universal coefficient formula. What about the second one? Is it correct? Basically, what do I have here? I have on P n plus 1 tensor Q. Okay, hom over Q. And here I have hom over Z, Pn plus 1 Q. Okay, so what's the relation between the two, if any? Well, firstly, if we have two vector spaces over Q, then is it true that every map between them, every map of abelian groups between them is a map of Q vector spaces? Ну, давайте вспоминать. Значит, у нас есть два Q-векторных пространства, вот и вот. Значит, правда ли, что отображение Q-векторных пространств между ними это точность то же самое, что отображение абелевой группы? Да. Значит, здесь важно, что в Q-векторных пространствах делить можно не просто, а однозначно. So we are able to erase the Q here and to write Z instead. Very well. So does the formula start looking any familiar, any more familiar, or less familiar? Yes. This formula resembles very much the Hom tensor product adjunction. So basically, Hom from something tensor something into something is the same as Hom from the first something to the Hom from the second something to the third something. So this Q is precisely Hom over Z from Q to Q, which is Q, as we've just seen. So the first equality is the universal coefficient theorem, and the second equality is basically the Hom tensor product adjunction. Okay. So there is an element of there is a group in the first Leray spectral sequence which is the group that we want to identify with the generators. Now, the Leray spectral sequence for this. Okay, so the Leray spectral sequence of the second. The second spectral sequence E2, 0, and plus 1 for the second. Is C plus K1 from the construction of Mn plus 1. And these are precisely the generators of M in degree n plus 1. So if we're able to construct the spectral sequences and prove that they're isomorphic starting from E2, then we have theorem 2. Now I want to construct the spectral sequences. Now, does the expression spectral sequence make any sense? Well, let's think. The okay. Well, the array to construct the array spectral sequence, we basically take the dumb filtration on on APL of sorry, the dumb filtration on the forms of xn, and we pull it back to xn plus 1, where the dumb filtration is just it's just the it's just eliminating consistent eliminating everything in degrees less than or equal 0, less than or equal a given I. And we can do the same for on the level of algebras, and then there is a way to map one algebra into another algebra so that everything is an isomorphism. Okay, no time. We'll do this properly next week. Okay, so everything up to the construction of the spectral sequences was hopefully more or less clear. We'll construct the both spectral sequences and the map between them next time. Okay, are there any questions? No questions. Okay, well then this is it for today, and we'll continue next week.